Now what we've used here without really knowing it is this thing called the method of undetermined coefficients, which basically just says that if you have an equation and you know what its template solution looks like, so we made the argument that if you had an equation where it's the second derivative plus ay equals 0, then our guesses were going to be y1 equals sine of something t, sine of bt, and y2 equals cosine of bt. Now we already kind of observed the pattern from our previous example that this was going to be the square root of whatever a is, but let's just go ahead and derive it. Let's just say that we didn't know what b was and we wanted to figure out what b value would make this equation true. So we took its first derivative, we took its second derivative, which would be negative b squared sine of bt. And we can do the same thing for y2 over here. I'm going to go ahead and skip y2 because it's the same thing. Now to find out what value of b would make this equation true, let's say we plugged it in. So we found that the second derivative plus ay has to equal 0. And now I'm not questioning the equality because I'm going to solve for the value of b that makes that equality true. So here we have negative b squared sine of bt plus a times y, well, y is sine of bt, and that has to equal 0. Now, if I factor out a sine of bt, or you just view this as, if you add these together, the coefficients are going to add. Right? If you have the same function, like terms, the coefficients add. But you could also look at it as, let me factor out a sine of bt. Now, the only way this is going to equal 0, this product, is if negative b squared plus a equals 0. And so if we want to solve for b, we get b squared equals a. And so b is equal to the square root of a. Now, it's really plus or minus. But we're just going to take the positive value for now. And the reason we're not going to take the negative is because if you take sine of, if you take, for example, cosine of a negative angle, so cosine of negative t is the same thing as cosine of positive t, and that's why we're omitting the negative in here as well. And the reason this is true is just because cosine is a symmetric function about the y-axis. So for this angle, it's the exact same value as for that angle that's positive. So that's why we're not taking the negative value as well. Now we will when we're not dealing with sine and cosine, but for sine and cosine, plus or minus the square root of a is not going to make a difference. So we'll just go with the square root of a. So you can see that the value of b that we're going to need here is the square root of a. And that's why up here we saw that the square root of 8 was a function of the fact that this was an 8 here, and if a was 8, then b had to be the square root of that number. So this is just another way to show it. Let's just take a look at one more example. Let's say that we had the mass is 3. We're going to say we have an undamped system. Again, if b is 0, it just means you have no damping force. And we'll just say k equals 17. So our differential equation is the second derivative plus b over m times the first derivative. Well, it's 0 over 3 times anything to give us 0, plus k over m, which is 17 over 3 times y equals 0. Now we know that it's going to be sine of the square root of 17 over 3 and the cosine of 17 over 3, t, but let's just say that we wanted to establish that. So we could formulate, and this is just going to be a good strategy to have when the functions are not always resulting in sine and cosine, but your guess is, I know it's going to be something of the form y1 equals sine of something t, and y2 is going to be the cosine of that same something t. How could we solve for that something? Well, once again, when we take the derivative, the second derivative of y1, we get negative b squared sine of bt. And let's just go ahead and do it in parallel over here for cosine. Its second derivative is going to be negative b squared cosine of bt. Now, to find out what value of b will make this equation true, all we have to do is take negative b squared sine of bt. That's my second derivative. So over here we'll have negative b squared cosine of bt, plus 17/3 of y, which is sine of bt. And same thing here, except plus 17/3 y, which is cosine of bt. And we know that that has to equal 0. And same thing over here, that has to equal 0. Okay, so when we add these two sine functions together, we're going to be adding their coefficients. We're going to be adding negative b squared plus 17/3. So that means that in order for them to add, we want them to add, we want those coefficients to cancel each other out and add up to 0. So if we solve for b here, we'll have b squared equals 17/3. And so b, we said we're with sine and cosine, we're not going to take plus or minus, we're just going to take the positive square root because of the symmetry of cosine. Similar kind of concept for sine as well. And then over here, we'll also be able to argue that the sum of the coefficients of the two cosines has to equal 0. So here we'll have negative b squared plus 17/3 equal to 0. You see that we're solving the same equation. We get b squared equals 17/3, and b equals the square root of 17/3. So that gives me two solutions, one of them being sine of square root of 17/3. So y1 equals sine of the square root of 17/3t, and y2 equals cosine of the square root of 17/3t. And of course, by superposition, we want to take any multiple of the first function plus any multiple of the second function. And now if we had some initial condition, we could once again go and solve for k1 and k2. We're always going to have, something for the initial position, and we're going to have something for the initial velocity. Sometimes you'll see it written like this. The initial position is written often as y0, initial position, and then the initial velocity you'll often see written as v0. Now, in our next lesson, we're going to look at, well, what if there isn't zero damping? What happens whenever you start to include damping into your model where it's not a 0 in front of the dy dt? Our guesses have to adapt a little bit more because sine and cosine are not going to work exactly. So we'll go ahead and stop there, and in the next lesson, we will get into how to solve these homogeneous equations with non-zero damping.